Welcome to the course on Power Electronics with Wide Bandgap Devices. Today I am going to discuss about the PCB part. So what are the constraints that we need to consider for designing high frequency PCBs for the wide bandgap device applications? So basically when we are going to consider wide bandgap devices, the operation of the converter will be at high frequency. If the operation is at high frequency, then there are several factors we need to consider for designing PCBs. Let's see what are these factors. So basically, if we are going to consider this PCB design, to achieve high frequency PCB, we need to consider some factors. So these factors I am listing down here. So the first is that minimum onboard noise. So noise is one of the important thing which affects at high frequency operation. So basically when the operation is at slightly lower frequency, the noises effect will be much less as compared to the high frequency operation. So we have to consider a PCB design where this noise effect will be less from the board itself. So we will see in details how this noise is coming from the board. So the second point is that minimum crosstalk. So crosstalk already I have discussed earlier in details. So basically crosstalk effect of one particular line to other line or one switch to another. So that effect we have to minimize. That also we will see in details. Okay. Then reduction of ground bounds. So basically what happens if all the connections in the PCBs are connected to ground at some point, so then we have to make sure that at every point there is a decoupling capacitor connected in order to reduce the noises from PCBs. So that is called ground bounds. Okay. Now fourth point is that simultaneous switching noise reduction during operation. So it can happen that there are actually multiple switches. So then we have to make sure the simultaneous switching are not happening. So basically there may be some gap between switching of one particular switches with respect to another switches. So that part we need to look after. Fifth point is that provide correct signal line so we have to provide termination of each signal line. So whenever there is a signal line, with respect to each line it will be having some impedance. So we have to actually provide termination for that particular impedance, otherwise noises will travel back and forth by using that impedance line. We will see in details these X points. So basically you can see these are the different points which is going to affect the high frequency PCBs for wide bandgap device applications. Now when we are considering these different effects, so then what we have to do? We have to provide some method so that we can reduce all these problems. So one of the important thing we need to consider is that board material. So whenever we are designing PCB or are actually PCBs are made, so there are like different materials we can consider. So based on the board material also it is going to affect the operation of the converter at high frequency. So board material is one of the important point. So board material, if we have to consider, so based on the material, what will happen? It controls how much noise and crosstalk is contributed from high frequency operation or fast switching operation. Input output signal. So basically this board material will give some force between the signals. So this force we can actually define as charges between two lines divided by permittivity of the board material. Now this force will cause some noises to be present in the board. So depending upon the board material, this noise can be more or less. And how this board material is going to affect? So you can see here, this is the term which is known as permittivity. It comes from the board material. So if this permittivity is high, so then force will be less. If it is less, then the force will be high. So basically signal can propagate faster if epsilon r is less. So this we can actually choose based on the availability of the board material. We can choose the lower permittivity material so that signal propagation will be faster. Okay. So now there is one important thing is that impedance. So basically what happens whenever any line is present in the board, so then that particular line will give rise some impedance. How we can define this impedance? This impedance we can actually define in terms of Z, which is equal to so you can see here, so there are different terms present. So these are all coming from the board itself. So H is the height of the board, T is the thickness of the board, and W is the width of the board, and epsilon r is the permittivity of the board material. So all this will give rise some impedance. So whenever there is a line, so then that particular line will have some impedance. Now this impedance need proper termination, otherwise there will be noise which will be traveling back and forth through this impedance. Okay, so now that termination can be done by using different method. So then let's see. So basically, in order to reduce, so these are the noises which can be present in the board itself, and at high frequency the effect of the noises will be more. So we need to provide a way to reduce these noises. So to reduce these noises, onboard noises, what we need to provide? Onboard noise reduction. So then what we have to do? We have to reduce crosstalk effect. Then signal integrity means we have to provide the signal path such that there is like signal. I have already shown you in the other lectures. So how the signal line should be? It should not be, the bend should be such that there will be less noises present. So basically straight bend can cause more noises to be present. So that is why the signal, whenever there is a bend point, so that bending should be such that noise effect will be less. Then power noise filtering. So every point we have to see. In order to filter this, so what we have to do, if there is a VCC signal, input signal, let's say VCC input, so that has to pass through LC filter. So LC filter generally it present ferrite bit, so and then it will be connected close to the C. The C is generally 10 microfarad in that range, and then the output will be connected close to the PCB board. So VCC source may be connected bit away from the PCB board. So then there can be this LC type of filter which can reduce noise between this source and the point which is connected to the PCB. Okay, that power, this is with respect to the power noise filtering. Now if we have ground bounce effect, so that generally comes during the switching of multiple switches. So like some switch it is turning on and off, simultaneously other switches are turning on and off. So that will cause the ground bounce effect. So now in order to reduce that, what we have to do? Again we have to connect filter. So decoupling filter. So basically if there are like multiple output which are connected and each are like switching simultaneously, then what we can do? We can actually connect capacitors with respect to each signal, right? So then it will reduce the ground bounce effect. Okay, now as I mentioned that there can be impedances in the line and which needs termination. So how this impedance termination is going to be? So basically if there is an impedance, we have to provide matching impedance for the termination so that it can reduce the noises due to this impedance present. So this termination can be of different type, means like this impedance termination can be classified in different types. So they are, the first one is simple parallel. So then here what happens, if there is a signal, so this signal is connected to the impedance which can be calculated by using this particular formula. So Z impedance. So this Z already present in the PCB board. This is the signal input. Okay. Now the signal output will be affected due to this impedance present. What we have to do? We have to provide the matching impedance. So now in this simple parallel method, so the matching impedance will be connected in the parallel. So that will be connected to the ground. So this is the matching impedance. Okay. Now there can be another method by using Thevenin type of termination. Now this is like active type of termination, source series type of termination. So another is the Thevenin parallel termination. So there what happens? So this Z will be present. Then due to Thevenin, so there can be two impedances connected this way. Signal output, signal input. So here in the first one, in simple parallel one, R should be equal to the value of Z. And in case of the Thevenin one, since it is R1 and R2, it is connected in parallel. So R1 parallel R2 should be equal to Z. So ultimately matching impedance we have to provide for the termination. Okay. Similarly, there will be active parallel, then series RC, then VCC series. Termination. So these all are the classification of the termination. This will reduce the effect of the impedance present in the PCB board. Okay. Now, if you see that like this is the diagram of like every path which is present in the PCB. So each line in the PCB board, it acts as a source and sink. So if you see here in this particular block diagram, it is shown source and sink, one with respect to the orange color, and it is connected to coupling path which is connected to another source and sink. So basically each line, if it is act as source and sink, and this is actually connected to coupling medium. What are this coupling medium? So this coupling medium, so basically coupling path what is shown here. So it can be either, let's say, capacitive or inductive or galvanic radiated power So now what happens? It can cause interference for this present of coupling medium. So this coupling medium can be capacitive, inductive, galvanic, radiated power. So anything it can be. So this line will interfere with any of this component and it will cause interference. Okay. So you see, so these are actually different component which generally affects the PCB board. So I have listed all these components. Also I have discussed earlier. So the first thing is that electromagnetic interference and electromagnetic compatibility. Basically EMI or EMC. So what happens? This EMI is the radio frequency energy interfering with the electronic devices. So this interference, as I have discussed in the previous slide, so it can be with any of the coupling medium. Okay, so this coupling medium will be present in the PCB by default. So this will cause EMI type of interference. Now EMC is the ability of a product to operate without causing or being affected by EMI. Okay, so we have to actually look after these two things whenever we are operating any system at high frequency. What is their EMI, and then what is the EMC of that particular system. If it is okay, then fine. Otherwise, we have to design filter in order to reduce the noises due to EMI. Okay. Now this filter, as I have discussed earlier, it will be in terms of LC. So there can be decoupling capacitor in multiple places, or there can be ferrite bits, or combinations of decoupling capacitor and the ferrite bits. Next is the clock signal. So basically clock signals are ideally square wave, but it is actually trapezoidal, because whenever we have provide any signal, like any type of signal, we decide it to be square wave, or we expect it to be square wave. But generally what happens, this turn out to be trapezoidal, like this. So you can see here the black one is something which we expect, but red one is something which we get. So due to this, so you can see here, so basically these are the places which will cause noises to be present. So this different, like the shaded portion which I have shown here, this part we have to see how to minimize this particular part. Okay, so harmonics depends on this rise and fall time of the clock signal. So as I have seen here, so basically these two shaded portion, it is due to the rise time and fall time of the clock signal, and it will cause harmonic to be present. Okay, due to the clock signal. Then third is the transmission lines. So basically traces on PCB, it acts as transmission line. It is not the power line, it is the transmission line of the PCB. So whatever line you are drawing in the PCB, that is PCB transmission line. And it is the one which decides signal speed, propagation delay, characteristic impedance, reflections and crosstalk. So now one of the important things is that signal speed or the propagation delay. So how to find out this propagation delay? So propagation delay can be find out. So basically it can be represented as V equals to 3 into 10 to the power 8 per second divided by root under epsilon r. So whenever any signal is flowing through the transmission line, so the speed of the signal will not be equal to the speed of the light. So speed of the light is given here. So how different it is going to be? So it will be affected by the permittivity of the board material. So you can see here the speed of the light divided by root under epsilon r. So this is the factor, it is going to decide how much propagation delay is going to be there. So for different board material or the different value of all the other parameter, this propagation delay can be different. Okay, and it is going to affect the signal speed. Okay, so let's say if there is a like any like PCB board which is having, let's say, microstrip 1 and microstrip 2 different types of the PCB lines and everything, if I decide, so let's say one system and another second one, so each is having, let's say, thickness 0.501. so this is the thickness. Then epsilon r, permittivity of these two board material, it is different. Let's say one is 3.046, another is 3.165, and then there can be other parameter also. By based on this parameter, we can actually find out the propagation delay. So the propagation delay So in by using other parameter, it is calculated as 581.7 for 1 picosecond for 100 millimeter, and another one is 593.1. So you can see, like, different bore material, different thickness of the PCB lines, all can affect the propagation delay. So we have to see that how to make sure this delay is not much for any. So now this signal speed and the propagation delay time, it depends on, you can see this fifth one. So signal speed on a PCB trace is less than the speed of the light, as I have told you. The propagation delay time is crucial for meeting timing and skew requirements. So that is why while designing PCB, we have to consider all these different factors. And if it is for high frequency, these factors becomes quite significant, because any delay in the signal, it is going to affect the operation of the entire system. Now, sixth one is the characteristic impedance reflections and the termination. This is with respect to the impedance, which I have already discussed in details. So reflection occurs due to the impedance changes in the signal change. So that is why we need proper termination. So the termination can be using anything like the simple, parallel, Thevenin, or active, any method you can use, so that we can actually provide termination for the impedance, so that there will not be any reflection. So proper termination technique, series, parallel, Thevenin, and AC termination, any of these we can use in order to provide the termination. But before that, we need to calculate the impedance. Unless and until we have the impedance value, we cannot provide the matching impedance for the termination, because for termination we need to provide matching impedance. Now another point is the crosstalk. So the crosstalk is the mutual influence of the two parallel traces, right? So the two lines, if it is there, so then one line can affect the other line. So that is why this type of crosstalk can be either forward or backward. So mitigation, how to mitigate this crosstalk? So keeping traces at least 2 times the trace width upward. So this is the point it needs to fulfill in order to reduce the crosstalk effect. Now differential signal. So if we have differential signal, then what will happen? One advantage is that if they have equal magnitude and opposite sign, then it will cancel each other's electromagnetic field. So that is one advantage of using the differential signal close to each other. The electromagnetic field will be actually cancelled. So this is important for achieving equal propagation delay time. Otherwise, the propagation delay for forward path and the return path may be different, right? So that is why it is very important to have the differential signal lines close to each other. Return current and the loop areas. The return current follows the lowest impedance path, and the large loop areas increase radiation and the EMI problem. Okay, to avoid slots in the ground reference planes to minimize the loop area. So that is why this part need to be looked after in order to provide the solution for this EMI problem. For this large loop areas, increased radiation and EMI related issues. Okay. Next is that PCB consideration during the circuit design. So essential consideration during the initial design phase to mitigate the EMI. Okay. The next point is the board stack up. So proper layer of the stack up can reduce EMI and improve signal integrity. Then one of the main important point is with respect to power and ground planes. So solid and continuous power and ground planes are crucial. That will actually reduce many effect, many signal related issues, and noises can also be reduced down if we have continuous power and ground plane. If it is not continuous plane, if it is not multi-plane, at least proper bus if we can provide where the power and ground planes can be provided in the, like, in a bus line, so that each signal where the termination is required, so it can be connected very easily, and also ground plane will be close to each of the termination point. Okay, so that will reduce the noise effect. So ground planes should have minimum slots to avoid the loop areas. Now in order to reduce the noises will be present in the PCBs. We have to place the decoupling capacitor in the multiple places. So placement and selection of the decoupling capacitors, it is very important for noise reduction. And then traces and wires and other PCB components, routing guidelines for minimizing EMI and maintaining signal integrity is very important, and proper via placement and trace routing strategies is required. So clock distribution strategies for clock signal distribution to minimize the delay and the EMI effect. So these are the references for this particular topic. You can just go through these references to know how to design the PCBs for high frequency operation. Thank you.